Hello, today it's my pleasure to talk about linear regression. So we're going to do a little bit of a statistics overview before we delve into linear regression, and then we're going to finish today with power regression. So what is regression? This is when you fit a curve to some data. The curve is not a perfect fit. Not all the data points will pass through the curve. This is the first one that we're going to investigate. So let's talk about statistics for a little bit. Let's say that we have some values, some y values. We've got n y values. The average or the mean is called y bar, and this is the sum of the y values divided by n. The median is the one when you take the y's and you sort them from minimum to maximum. The one in the middle is called the median. I like to think about the median and the mean. I like to think about them because the mean can kind of get shifted away if there's some really far out value in one of the y's. The mode is not one I use often, but this is the one that would occur most frequently in your data. Max is pretty straightforward. That's the maximum. And the min, that would be straightforward. That'd be the minimum. Okay, so range is when you take the max and you subtract the min. Delta is where you look at the mean and you look at how far the max and min are from the mean. This is a big one here. The sum of squares of residuals. That's one that we're going to rely on to tell how good our fit will be. Standard deviation is where you take the ST and you divide it by n minus 1, and then you take the square root. So I've always wondered, why is it n minus 1 and not n? Well, it turns out that we only have n minus 1 independent numbers, so that was finally enlightening for me to get that standard deviation. Okay, so let's take a look at linear regression. So in this situation, let's look at an example where we have 10 points, 10 x, quote-unquote, xy pairs. Our x is going to be some velocity data, and our y is going to be some force, drag force, for example, data. Okay, so we're going to be looking for a line that tries to go through this data, and we're going to look at it in terms of a y-intercept, x a naught, and a slope, a1 times x. So we want to find the best a naught and the best a1 that will go as best as possible through this data. So here's our data kind of spread out, and there's kind of how the line that we're going to find fits to it. Okay, so one thing here I'm not going to fret too much about is, wow, these the a naught and the a1 they certainly would have units, but I'm not going to fret about that right now. Okay, so let's see if we can figure out how we get these coefficients, the a naught and the a1. Well, the first thing is let's set up some residual errors. So that would be between the data points and then the fit being described by the y value of our line, a naught plus a1 times x sub I. So then what we're going to do is we're going to try to minimize the sum of squares of the residuals. So that is going to give us an s sub r, capital S sub r. And we're going to try to minimize the sum of squares of residuals. So obviously this is going to be a real value that no matter how our line looks, it's going to be a real value since we're summing some residuals and we're going to square them. Okay, so let's see, if we have this function right here, how would we minimize that? We have a function and we want to minimize it. And we want to minimize it based on changes in a naught and a1. Well, then what you want to do, of course, is you want to look at the derivatives. You want to take that the partial of SR with respect to A naught, and then you want to take the partial of SR with respect to A1, and this is what you get. I mean, if you focused over here on just A naught, looking at that function, then of course you're going to have the minus 2, because it's that function part there squared, and then you're going to have a minus, and then you're going to have the stuff that's in the parens, and nothing else, since A naught is just a single factor, single power. So that one's pretty straightforward. If we're going to look at what happens with the A1 when we do the partial of SR with respect to A1, we're going to have that minus 2 again because of that and that, but then we're going to have an extra x here that multiplies the factor of what's between the parens because of the x right there. Okay, so we have two partials, and we would want to set those equal to 0 to solve for them. And to be honest, the minus 2's that lead here are irrelevant, superfluous, since we're going to set it to 0. And you end up with these two equations right here. Very nice equations, and you set those equal to 0. So we're going to have a summation of y sub I and a summation of x sub I, y sub I. So we could actually take those over to one side. We can move, or you can think of moving all of the minus terms over to the left, and that's kind of how it's written. And then we can kind of think about A naught being an unknown and A1 being an unknown. So we almost see the matrix right here that I have over here. So this is a matrix representation right here. This is the matrix representation of these two discrete equations. So it's very, very nice, very, very compact presentation. So we would know, obviously we would know n, and we would know the x sub I, so we would be able to sum those very easily. And then we could sum the individual x sub i's that are squared. We could sum those very easily. Summation of y sub I, something you would know because you have the data. And then summation of the cross, the xi, yi. So we know the right-hand side. We know this matrix. And it remains to solve for the A naught and the A1. Very straightforward. And here's a solution for A1. And very, very easy to get this. If you think about Cramer's rule, and you kind of look at this matrix here, the matrix equation, the denominator here is actually the determinant of this matrix. So you would have n times summation of x sub I squared. That's that first term. And then you would have minus the back diagonal, the summation of x sub I times the summation of x sub I, or the summation of x sub I quantity squared. So that's the denominator. And then remember, for Cramer, we're trying to solve for A1. So that goes with the second column. So I'd take that second column and replace it with the right-hand side. So that would be n times summation of x sub I, y sub I. That's that first term. And then I would subtract the summation of x sub I times the summation of y sub I. That's the second term. So a sub I, straightforward to get that. A sub 1, very straightforward to get that. And then to get a sub naught, you look at the first equation here, which is exactly the same as the first row of the matrix representation. And if I look over here, I would have a sub naught. I just divide through by n. And then I could put this term over on the other side. And I would have summation of y sub I divided by n, which is y bar. And I would subtract a sub 1 times x bar, which is the sum of x sub I divided by n. So a sub naught is very easy to get. A sub 1, very easy to get. Oh, and then summation, the sum of squares of residuals, S sub R. So we're gonna use these capital S's in a moment. This I refer to this sort of matrix representation as a key result. Okay, so here we're going to put this to good use. We're going to take our data that we were given and really just kind of tabularize it, where I have x sub i's and then I have the sum of x sub i's. I have y sub i's and then I have the sum of y sub i's. X sub I squared, 10 times 10, 20 times 20. Okay, do all of those, and x sub I, and then I sum that, x sub I. And then I do the crosses. 10 times 25 is 250. 20 times 70 is 1400. I do each one of those, and then I sum that. So now with these sums, I'm ready to go. I come over here. I've got my n, and then which is 8. I have 8 points. And I'm going to multiply by the sum of x sub y sub I, which is this number. I'm going to subtract the sum of x sub I, which is 360, times the sum of y sub I, which is 5135. So that takes care of the numerator. Denominator, I have n again. And then I have sum of x sub I squared. So that's going to be 20,400. So you want to make sure that you keep this, the 20,400, distinct from the sum of x sub I, quantity squared, which is going to be 360 squared. So very different here. So that fills out the denominator, and I get 19.47 for my slope. And then then a sub naught is going to be the y bar minus a1 times x bar. So y bar, or sum of y, is going to be 5135 divided by n. That's the first term. Got the minus the slope, and then the sum of x, 360 divided by 8. So I end up with minus 234 at 28, which is that's what the book had. Okay, so we want to quantify errors for linear regression. We're going to use that capital S sub R, the sum of squares of residual. Sometimes you see the standard error of the estimate, sort of the same thing as standard deviation. And what you do there is you take the S sub R, like we used the ST before, we're going to use S sub R, and we're going to divide by n minus 2 this time. And the reason why it's n minus 2 is because now that's the number of degrees of freedom we have after we've established A naught, A1. Okay, so what we want to do is we want to compare what I'd like to do is compare ST with SR, and that is called the coefficient of determination. So this is kind of my metric that I look at, and hopefully you'll see why here in a few minutes in our example. And what that does is it compares ST with SR, but it bases it in a relative way to ST. So here's kind of the idea. I got this from the book. So the basis of ST is where you just have that flat mean line here in your data, and you're going to compare how the data looks relative to that. So that's the ST, the sum of squares of residuals for the mean. So it would look like that. And then if you were to look at the line, so the line should do better. The line should do better than just the mean. And then the residuals are going to give you some value, some distribution like that. The sum of squares for the residuals of the mean is going to always be bigger than the sum of squares of residuals for the line. So we're going to always have that. And then the coefficient of determination then is going to be S sub t minus S sub r divided by S sub t. Now, if the line is perfect, that means S sub r would be 0, and then the r squared would actually be 1. So that would remove all of the uncertainty if you were able to do that with the line. So an r will vary between 0 and 1, 1 being like a perfect fit for the line. So this gives us a good measure. Okay, so if you have a really good fit, as I was saying, then you'd have a high R, and if you have a fair fit, then you have a low R. Okay, let's see how we do for this data. What I did is I created some other columns that go with the XY data. I created a column that represents the Y value of the line fit, and that's going to be A0 plus A1 times the individual X sub i's. So this is the fitted data. I created a column that is going to have my residuals with respect to the mean, the Y bar. And I do those, so the residuals are going to be those individual differences squared. Then I sum them, so this is going to be my S sub t, with respect to the sum of squares of residuals with respect to the mean. So that's what that is. And then I take the individual y's and I subtract off the fitted data. So this is going to be the residuals with respect to the line. And then I sum those. So this is going to be the sum of squares of the residuals for the line. And that's going to be the 216, 118. That's going to be my S sub r. So you see I've shown the standard deviation calculation and also the standard error calculation. Those aren't used for me as often as the S sub t, S sub r. So I look at my coefficient of determination. That's going to be S sub t minus S sub r divided by S sub t. And that's going to look like I have removed 88% of the uncertainty by doing that linear fit. Sometimes you see the standard error used, and sometimes you see the correlation coefficient used. Now I'd like to take the concept of linear regression and extend it to some different nonlinear examples. And the first one that I would like to talk about is what I call a power regression. And this is where you have y is equal to an alpha 2, say, times an x to the beta 2, let's say, for example. And anytime I see a variable to a particular power multiplied by a scalar, I immediately think that we're going to be able to do that exponent is actually going to be a slope in a log type of plot. I immediately think this. I've seen it so many times. So the reason I know that is if I take this expression, the alpha 2 x to the beta 2 equals y, and I take logs of both sides, I'm going to have log y and then log of that right-hand side. And I know that the log of a product is the sum of the logs, so I end up with log of alpha 2 plus the log of x to the beta 2. And since I've got that beta 2 in there, the x to the beta 2, I know I can pull that exponent out to scale the log of x. And this ends up looking like this in a log plot where the log of y now is your quote-unquote y. The log of x is your quote-unquote x. The log of alpha 2, you could consider that like a y-intercept. And then that beta 2 is actually going to be the slope in your log plot. So what I'm going to call these things is I'm going to call that slope my a1 comma log, if you will. And I'm going to call the y-intercept, I'm going to call that a sub naught, quote-unquote, log. Okay, so let's go put that to use with our example. And the reason why I'm kind of excited about this is because that force is the drag force. I kind of think of it, with respect to velocity. drag force is proportional to velocity squared. So I'm kind of anticipating that I'm going to get that beta. That beta 2 is going to be it should be near a 2 if this were correct. So what I did is I created some additional columns. I've got a log of xi, I've got a log of yi, and then I have a log of xi quantity squared for each x sub I piece. And then I have a log xy times log of yi. So let's go ahead and see if we can do this. Yeah, this is what I was saying, is that the drag force should be proportional to velocity squared. All right, so let's put our equations to use here. So my a1 log, I'm just going to take my original equation and replace x sub I with log of x sub I. And I'm going to replace y sub I with log of y sub I. And I have to be kind of careful here when I'm dealing with the x sub I squared and the summation of x sub I quantity squared. So I've tried to be very, very disciplined in how I did this, and we'll see how it works out. Okay, and then I have, of course, the a sub naught log here, and let's see how this kind of works out. So looking at my a1 log, I'm going to have n, which is 8, and then I'm going to have the summation of log xi, summation of log xi times log of yi, so that would be this column, and that summation is 33.622. And then I subtract off the summation of the log of xi, which would be here, 12.606, times the summation of log of yi, so that would be here, 20.515, so that's my numerator up here. And then I divide by the denominator, so that's going to be 8 for n. And then I have a summation of log of xi squared, summation of log of xi squared. So that's going to be this. So I've got log of xi squared, and then I've got the summation of that. So yeah, that's the correct thing. Log of xi squared, sum that, yep, it's going to be 20.516. And then I'm going to subtract off the sum of log of xi, that quantity squared. So that's going to be the 12.606 squared. So trying to be very careful I get that right. And I get 1.98, which is nearly 2. And then I take this a naught log. It's going to be my y bar, which is going to be log of the yi squared divided by 8, minus the slope, a1 log. And then I'm going to have summation of log xi divided by n. So that's going to be my x bar. So I end up with this minus 0.562. Okay, so I think I got something. Let's see. So yeah, so we've used these to get the a naught log and the a1 log. And this means that the fit is going to be log of f is equal to that offset minus the beta naught, or the beta 2, or the a1 log times log of v. And if I kind of put this together, this is going to be my alpha 2. There's going to be my v, which is my, my x is my v, and then I have my beta 2, that's going to be the exponent, which is going to be the slope here. Okay, so here's the data, how it kind of fit. So the raw data is shown as diamonds. I put my linear fit as a green line, and then I did a power fit. I did the power fit in 2 different ways. I'll show you the code in a minute to check it. And it's very interesting that the line looks better than the power fit. Power fit has this point. The power fit hits this point very well and hits that point better than the line, but the line does better on this point and this point. The power fit does okay here. So this point, these are two outliers, and then this point's kind of closer to the line. So it'll be very interesting to compare how the line does relative to the power fit. So let's look at the code. So here's the code that I used to draw that figure. And let's see if we can put it together. The very first thing I note is I take my theory and I put it to good use, code it directly from my theory. So I've got my n, so this is my numerator, n minus the sum of x so this dot star is an element multiply y. So there's my data, my x data and my y data. So obviously I get the length of x is going to give me the number of data points. But this dot star is something that you want to pay attention to. So that's an element-wise multiply. I do a sum of that. So that's going to take care of this first term. And then I subtract off the sum of x, sum of y. So it's going to be the second term in the numerator. Denominator, n times the sum. And this dot caret, that's going to take every element of x and square it. And then it's going to sum that. So that's this part. And then do a minus, a sum of all the x's, and then square that quantity squared. So that's the second term in the denominator. So a1 is taken care of. A naught is going to be the y mean, that's this, minus a1 times the x mean. So that's that. So that's my just straight from my theory. And then I have a y fit array. So that's going to be a naught plus a1 times x. So it's going to give me an array, same size as x. I'm going to get y fit. And then I went ahead and did a y bar just to kind of have that data. So I encourage you to check out what the repetitive matrix function or repmat function, how that works. So I've got a y bar that I could have plotted, but I commented that out. So that's how I could do that. And I earlier had returned. So this is all commented out. So now I'm going right into figuring out how the line fit looks. So I have the ST is going to be the sum of y minus y mean each. So these are my residuals. Y minus y mean is going to be an array. I take each one of those to the 2 power, square each one, and then I sum that. So that's sum and square of the residuals. Go ahead and plot out what my standard deviation is. And then I do the same thing for the y relative to the y fit, which came from this. So these are my residuals, and then I take those, square each of those. So these are my residuals for the line, and then I do the sum of those. So that's my S sub r. And then I did the standard error. And then this is the one that I'm really interested in, the coefficient of determination. And then I went ahead and looked at the correlation coefficient. So this is kind of looking at that data, comparing it with what my earlier slide showed. It's good to kind of take the code that you generate and make sure that it agrees with your theory. So here's the ST equation, and that's exactly how I programmed it. Y minus y bar or y mean, each one squared, and then the sum of that. And then the SR will be the yi, the y, minus the y fit quantity, each one squared, and then you sum that. So that's SR. And then the coefficient of determination is going to be my r squared. I'd call it R2 here. That's going to be ST minus SR over ST. So very nice. And then we kind of go in the code. We go straight into looking at the power regression. And for that, I went ahead and did a log 10 of x. So some of these MATLAB functions, they will return. They are configured to return an array of the same size as what you gave it. So if I give it my x, which I have up here, and I give it my y, which I have up here, then it's going to return the log 10 of each of those elements. And this is going to return the log 10 of each of the y elements. And just kind of as a sanity check, I wanted to see, hey, will this, the x log that I get, if I were to square each one of those, does that give me what I thought? And it did. I just did a sanity check. So it's kind of set me up for success where I could go and implement my A1 log and my A not log. And basically, I'm just going to rely on the same equations here. It's going to be n times the sum of x log dot star. So the dot star, again, that means that I'm taking each one of the x logs and multiplying element-wise with the y logs. So I'm going to get x log times y log, and I'll have n of those, and I'm going to sum those. So that's what this wants. And then I'm going to subtract off the sum of the x logs times the sum of the y logs. And that's all going to be setting up the numerator. And then I divide by the denominator, so that's going to be n. And then this is where I need to be careful. That's why I kind of tried that one out to make sure it made sense. So I'm summing the individual x logs being squared. So that's what that is. And then I subtract off the sum of the x logs quantity squared. So that's what I'm doing there. And then for the A naught log, I'm going to use the A1 log and then the means of the y log and x log. So I get my y fit in the log way. I looked at this twice, looked at two different versions of this. I've got a y fit log and a y fit log and then a y fit log 2. So they're a little bit different. This one is looking more like the alpha 2 times x to the beta 2. That's what that one's looking like. Or I just look at the y fit log in a log kind of format. And if I were to use y fit log, then I would just go 10, take each one of those to the y fit log power. That would be my red sort of power curve. And then I said, well, what if I use the alpha 2 times x to the beta 2 type of format, and that's going to be my y fit log 2. I did that in blue and I did it with dashed. I just was very curious to see if this red curve would be the same as the blue curve. And it turns out that it was. So this was the graph that I just showed you how to plot. Okay, and then I did some limiting so it would kind of make it look nice. So that's the code, and the code goes with certain theory. And that pretty much wraps up our idea here of linear regression coupled with the power. So when you've seen some statistics type stuff, you've learned about the linear regression, power regression, we saw some code. So hopefully you've enjoyed it.